Hello students, welcome back to another geometry video. This video starts chapter 12, and chapter 12 is all about probability. So, your entry task asks you to think about what is probability, and can you give an example of the probability of something? Now, if you haven't had much exposure to probability, maybe you're like, I don't know, but I want you to pause the video and think about it. What do you think probability is? Try to give an example of what probability is. So pause the video, do that, unpause it, and let's talk. What is probability? Maybe you've heard of the example of flipping a coin. If I flip a coin, I can land on heads. It can land head side up, or it can land on tail side up. So there are two possibilities for what could happen. I could have heads or I could have tails. So the probability that either one happens is 1/2. Or we say, because one out of two possible options, heads or tails, and there's two options. So we say there is a 50-50 chance. 50% chance of heads, 50% chance of tails. So when people say, oh, 50-50 chance, it means that both outcomes, both heads and tails, are equally likely. So the probability is like the likelihood or the chance that something will happen. Now we're going to get into the more fancier mathematical definitions of probability, but for now, probability is like the chance that something will happen. There's a 50% chance that I could flip the coin and it'll land on heads, and there's a 50% chance that it will land on tails. You might also thought of the example of rolling a die. Plural is dice, singular is die, so you might have thought about rolling a die. And there are 6 possible outcomes for rolling a die. And we're going to talk about more of that later, but you might have thought of the example that there's a 1/6 chance of rolling a 1 if we roll a 6-sided die. So those are a few examples, and we're going to talk more about those examples in the future. Okay, 12.1, the first part of chapter 12, is about sample spaces and probability. So we're introducing you to probability, and we're going to talk about sample spaces. Now, I know you don't know what that is yet, but we're going to talk about it on the next slides. So, our learning target for this lesson is that you know what sample spaces, theoretical probabilities, and experimental probabilities are. So there's 3 things that you need to know about after this lesson. 1 is sample spaces, 2 is theoretical probabilities, and the 3rd is experimental probabilities. Our success criteria is that you can use sample spaces to find theoretical and experimental probabilities. So you're going to use this first vocab word to find the next 2 concepts for this lesson. So let's jump right into it. Vocab, probability experiment. So if you run an experiment, if I am testing to see whether plants will live better if I feed them water or Coca-Cola, that's an experiment. I'm testing something. So a probability experiment is an action or trial that has varying results. Like if I feed plants soda instead of water, the results will vary between water and soda. The plant might live longer. It might live shorter. So that's like experiment, right? That's a different type of experiment. But when we think of probability experiments, we think about something like flipping a coin. It has varying results. I could get heads or I could get tails. We could think about rolling a die, like we talked about on the first slide. I could roll a 1, 2, 3, 4, 5, or 6. There are varying results. So a probability experiment is just something we could do that has varying results. I could spin a spinner and it lands on a color. Something like that. So, an action that has varying results. Outcome. You heard me say this on the first slide. An outcome is the possible result of a probability experiment. So, if I flip a coin, that's a probability experiment. An outcome is a possible result of that. A possible result of flipping a coin is heads up or tails up. The outcomes for rolling a die are 1, 2, 3, 4, 5, or 6. If we're talking about a 6-sided die. So outcome is just what could happen if you run this experiment. I could get heads, could get tails, could roll 1, 2, 3, 4, 5, or 6. Next vocab word is an event. You're going to hear us talk more about this as we talk about probability. We take the probability of events. So what is the probability that you win the lottery? What is the probability that we land on heads when I flip a coin? So an event is a collection of one or more outcomes in a probability experiment. So collection of one or more outcomes. So if I roll a die, there are many outcomes, right? The outcomes we talked about were 1, 2, 3, 4, 5, or 6. So I could say, what is the probability that we land on 3? Now that's one outcome. One outcome is landing on 3. I could say, what's the probability of rolling an odd number? Well, now we're talking about it could be a 1, it could be a 3, or it could be a 5. Because all of these are odd numbers. So that is more outcomes in a probability experiment. So an event is just something that could happen. What is the probability that if I pull a card out of a deck of cards, it is a heart or it is a spade? It's just something that could happen in a probability experiment. Collection of one or more outcomes. Okay, our last vocab word for this section is sample space. This was in our learning target and our success criteria. We are going to use sample spaces in all of our examples today. So the sample space is the set of all possible outcomes for an experiment. So if I flip one coin, I could get heads or I could get tails. So the sample space is heads or tails. There's only two things in that sample space. But if I flip 2 coins, well, I could flip heads both times. I could flip tails then heads. I could flip heads then tails. Or I could flip tails both times. So there are 4 things in the sample space for flipping 2 coins. So the sample space is just all of the possible outcomes. What could happen? What are all the things that could happen in this experiment? Okay, let's do our first example and let's find a sample space. So we flip a coin and we roll a 6-sided die. How many possible outcomes are there in the sample space? List the possible outcomes. Okay, there are multiple ways to list possible outcomes. We can make a tree diagram. We could make a table. There are many ways that we could list out all the possible outcomes. For this one, let's do a tree diagram, because if I flip a coin, I can get heads or tails, right? So first, For the first part of this experiment, there are two outcomes. I can flip heads or I can flip tails. Then, depending upon which one of these things that happens, I could flip heads or I could flip tails. After I flip one of them, I'm rolling a 6-sided die, which means I could roll heads, or excuse me, flip heads, and then roll a 1, 2, 3, 4, 5, or 6. And the same thing happens after I flip a tails. I could roll a 1, 2, 3, 4, 5, or 6. So, all the possible outcomes, we have, I could do heads and then 1, 2, 3, 4, 5, or 6. So there are 6 possible outcomes if I roll, or excuse me, if I flip heads. And if I flip tails, there are also 6 possible outcomes. Now, I could flip heads or I could flip tails. So together there are 12 possible outcomes. I could flip heads and then a 1, 2, 3, 4, 5, or 6, or I could flip tails and then a 1, 2, 3, 4, 5, 6. So all together, there are 12 possible outcomes. And when it says list the possible outcomes, we have heads and then a 1, heads and then a 2, heads and then a 3, heads and then a 4, heads and then a 5, heads and then a 6, and so on. Tails, then a 1, tails, then a 2, and so on. So those are all of the possible outcomes. Now let's check and make sure that we were right. They did the same tree diagram that we did, and they saw we could flip heads or tails, and then when we roll the die, we can get a 1, 2, 3, 4, 5, or 6. And same on the tails side. So, the sample space has 12 possible outcomes. Heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. And tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Okay, and you can use shortcuts when you're writing these things. You can use abbreviations, so you could just write H1, H2, H3 if you didn't want to write heads every time. As long as, you use H for heads, not like P for heads. Keep it consistent. Okay. Another vocab word, probability of an event. So we talked about this earlier when we talked about events. We can find the probability of an event. And the probability of an event is a measure of the likelihood or chance that an event will occur. And we talked about this on the very first slide when we said, what is probability? What do we think probability is? Well, it's the likelihood or the chance that an event will occur. So for example, when you roll a 6-sided die, the probability of rolling a 4 is 1/6, because there are 6 outcomes, possible outcomes in our sample space, and 4 is just one of the 6 outcomes that we could have in that sample space. Okay, next, that's what probability of an event is. Now we're going to talk more specifically about theoretical probability. This was something that we talked about in our learning target and our success criteria. We need to know what theoretical probability is, and then we need to be able to use sample spaces to find theoretical probabilities. So, the theoretical probability, and don't worry, these are the math words, but we're going to break this down. The theoretical probability is the ratio of the number of favorable outcomes to the total number of outcomes when all outcomes are equally likely. That was a lot of words, so let's break it down. For example, you flip a coin. The theoretical probability that the coin lands heads up is, and we write it, the probability of flipping heads, that's how we write it, is the number of favorable outcomes. What a favorable outcome is what you want to happen. What you want to happen. So we want it to land heads up. So the number of possible outcomes that we want, in this case, it's just one. We want heads. Not heads and tails, just heads. So there is one possible outcome that we want. We just want heads. And then the total number of outcomes. So what are all the things that could happen? So this is all the possible outcomes. So the total number of outcomes is heads or tails. So we have two. We have two possible outcomes, but we only want one of them to happen. We just want heads. So the probability of flipping heads is 1/2. Now, it says when all outcomes are equally likely, and that's because this is not true. If you have a coin that is rigged, you have a coin that, oh, it's shaved off on one side so that you always land on tails, then that's not fair. Then it's not a 1/2 chance because you've tinkered with things. So it needs to be equally likely that you'll land on heads or tails in order for this theoretical probability to work. So that was a lot of words. Now let's see an example. Let's see an example of what this looks like. So example 2 is finding a theoretical probability. This was part of our success criteria, that you need to use sample spaces to find theoretical probabilities. So a student is taking a student taking a quiz randomly guesses the answers to 4 true or false questions. So there are 4 questions, and they are true or false. I'm just making some notes so we can know what's going on here. What is the probability of the student guessing exactly 2 correct answers? Have you ever done this before? Have you ever been taking a quiz or a test and you just kind of randomly guess, oh, this one's A, that one is D, this is true, that's false? What's the probability that you get exactly 2 right? You could find out what the probability is that you pass. And I'm going to show you how. So, the probability of guessing exactly 2 correct answers. Okay, so in order to do this, first we need to find the sample space. Step 1 is find the sample space. Because the sample space is all the possible outcomes. All possible outcomes. You'll remember that's what the sample space is. If we find the sample space, well, on the bottom of our fraction, when we're finding the probability of something, the bottom part of the fraction is the total number of outcomes. The bottom is our sample space. So, we need to find the sample space so that our fraction can have whatever number it is, on the bottom of our fraction. So, the sample space. We have 4 questions that are true or false. So, what are all the things that could happen? Well, you could get them all wrong. You could answer question 1, 2, 3, and 4. You could answer them all wrong. You could. So that is a possibility. This is one possibility, answering them all wrong. Now, you could answer 1 right. You could get the first one right, and then you could get the rest of them wrong. Now, you could get 2 right, 2 wrong. You could get 3 right and 1 wrong, or you could get them all right. So, these are some possibilities, and you might think these are all of the possibilities. I could get 1 right, 2 right, 3 right, 4 right, none right. But it goes a little bit further than that, because when we say you could get 2 right, if you just write it like this, you're not taking into account that you could get the first one right, the second one wrong, the third one right, and the fourth one wrong. This is a different possibility than this. These are different possibilities, which means that both of these are in the sample space. So, we need to write out the order, and this is something that you'll hear in probability. Order matters, or order doesn't matter. In some problems, order matters, and in some problems, order does not matter. For this problem, the order does matter, because you can't get the first question right twice. That wouldn't make any sense. So we need to write out all of the possibilities. There's only one way to get all of them right, so we don't have to rewrite anything there. But when it comes to getting one answer right, it could be the first one, it could be the second one, it could be the third one, or it could be the fourth question. If you get one of them right, you could get the first question right, you could get the second question right, you could get the third question right, or you could get the fourth question right. So all of these are possibilities. And we kind of already talked about this, but there's still. So we could get the first one right, the next 2 wrong, and the last one wrong. We could, let's see, we could get the first one wrong, the second one right, the third one right, and the last one wrong. We could get the first 2 wrong and the last 2 wrong. Did I get them all? Oh no, we could also do wrong, right, wrong, right. I think that's all of them. And we'll find out. We can go back and find out. Right, right, wrong, wrong, right, wrong, right, wrong, right, wrong, wrong, right. Yeah. So these are all the possible ways that we could have 2 R's, 2 W's, getting 2 right, 2 wrong. Now, if we get 3 of them right, we could have the first one be wrong, the last one be wrong, we could have the second one be wrong, or we could have the third one be wrong. So there's 4 possibilities there. And then there's only one way to get them all right, right? No matter how I reorder these, it's going to be the same each time. So this is our sample space. We found the sample space. This is it. Now let's count up how many things are in our sample space. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 things in our sample space. So the probability of exactly 2 questions right is something out of 16, because 16 is all of the possible outcomes. Now, how many times could we get exactly 2 right? How many ways could we get exactly 2 problems right? Well, if we look at 2 right, 2 wrong, there's 1, 2, 3, 4, 5, 6. There are 6 ways that we could get 2 problems right. So, the probability of getting exactly 2 right is 6/16. Or, I think we can reduce this fraction. If I divide the top and bottom by 2, I get 3/8. So the probability that you get a 50% on your test is 3/8. That's not a super great chance. That's not super great. 3/8, that's less than half. Better study. Okay, so let's review, let's recap. There was a lot that happened in this problem, so let's recap. We found the sample space because in order to find the probability, we needed to know all of the possible outcomes, because that's the number that goes on the bottom of our fraction. So we listed out all of the possible outcomes. Here is everything that could happen. I could get all 4 questions right. I could get one of them right, and it can be any one of the 4 questions, the first, the second, the third, or the fourth. I could get exactly 2 right. It could be the first 2, it could be the first and the third, the first and the fourth, second and the third, second and the fourth, or the third and the fourth. I could get 3 of them right and 1 of them wrong. Could have gotten the last one wrong, the first one wrong, the second one wrong, or the third one wrong, or I could have gotten all of them right. So we listed out all of the possible outcomes, and 6 of them included 2 right answers. So we put a 6 on the top of our fraction, and we reduced it to get 3/8. Let's take a look at their answer. So they found the sample space, and they made a table similar to ours. They could have gotten 0 right, 1 question right, 2 questions right, and exactly 2 correct. This is what we care about. So they made a special note that this row is the one that we care about. And they used I for incorrect, and they used C for correct. So we used right and wrong, they used correct, incorrect. 3 right or 4 right. Now, number of favorable outcomes. Favorable outcomes is getting exactly 2 correct. So they had a 6 on the top, because that's how many? 1, 2, 3, 4, 5, 6 possible ways that we could get 2 answers right. And then they reduced to 3/8. And they also put it in a percentage, 37.5%. Sometimes a percentage is easier to understand than a decimal. Okay, wonderful. That is theoretical probability. Let's move on to experimental probability. So, the experimental probability is a little bit simpler, but it's also not as accurate. So, the experimental probability is the ratio, and remember, ratio is kind of like a fraction, the ratio of the number of successes or favorable outcomes to the number of trials in a probability experiment. So, let me show you an example, or give you an example. In 100 trials of tossing a coin, the result was heads 56 times and tails 44 times. So the experimental probability of tossing heads is 56 over 100, or 0.56, which is 56%. So here's why I say experimental probability is sometimes easier to find, because you just take, oh, this is how many times it happens, divided by how many times we did the thing. It can be sometimes easier to find, but it's not as accurate. We know that the probability of flipping heads is 50-50. It's a 50-50 chance that you get heads or tails. So the experimental probability can be easier to find, but not as accurate. Let's now jump into our last example of this lesson, where we find an experimental probability. Each section of this spinner shown has the same area, which means that we have the same chance. There's a 1/4 chance that we land on any of these. Well, the theoretical probability is that there's a 1/4 chance, because there are 4 colors, right? Red, yellow, blue, and green. There are 4 possible colors we could land on. So the probability of landing on one of those colors is 1/4. So the theoretical probability is 1/4. Actually, let's make a note of that so that we can compare in the end. Theoretical probability is 1/4. for any one of the 4 colors. The spinner, this spinner was spun 20 times, and the table shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical probability? So which one of these has an experimental probability that is equal to 1/4? Well, the experimental probability for red is 5 out of 20, because we spun it 20 times. Now, if I reduce this fraction, I divide the top and bottom by 5, I get 1/4. Hey, that's the same as the theoretical probability. Cool. So red has the same experimental probability as it does theoretical. Now, green is 9 out of 20, because we spun the spinner 20 times. And 9 divided by 20, I can't reduce that fraction. 9/20 is not equal to 1/4. It's bigger than 1/4. So green does not have the same experimental probability as it does theoretical. Blue, Blue is 3 out of 20. Can't reduce that fraction, not equal to 1/4. And yellow is also 3 out of 20. So the only one that has the same experimental probability as it does theoretical probability is red. Let's check and see if we were right. Probability of red is 5/20. Probability of green is 9/20. Blue is 3/20. Yellow is 3/20. The experimental probability of stopping on red is the same as the theoretical probability. Okay, so you can see that experimental probability is a little bit easier to find than theoretical probability sometimes, but it's not as accurate. Not as accurate. Okay, that is all I have for you today. Remember that if you have questions, come back to our Google Meet link, come to office hours, find a way to get your questions answered, email me, talk to me. I am so happy to answer your questions. Now, these are not necessarily your homework problems, remember, but these are some problems you can do to practice the skills you learned in this video. Remember, the skills that we learned, our success criteria was to be able to use the sample space to find theoretical and experimental probabilities. So, you can try these problems to make sure that you know how to find theoretical and experimental probabilities using the sample space. But remember to do the homework that your teacher has assigned you, not necessarily this homework. Okay? And of course, let's end our class, our lesson, with a launch, shall we? So this launch comes from Maya Angelou. I love Maya Angelou. And she says, "My mission in life is not merely to survive, but to thrive." So you don't want to just survive life. You don't want to barely scrape by, like living paycheck to paycheck and barely passing your classes. You want to thrive. And now life isn't all about money and getting good grades. There is much more to life than money and good grades. So what does it mean to thrive to you? What does it look like to you to thrive? Is that getting really good at beatboxing? Is that having the best Minecraft world you've ever seen? What does it look like to thrive in your life? Let it be your mission to thrive, not just to survive, not just to have an okay life. You want to have a fabulous life. So how can you make sure that you are thriving and not just surviving? Something I want to leave you thinking about today. That is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day. And thanks for being here. Thanks for watching. Bye.